Welcome. Thank you for coming to our presentation on our NERS or Mapping and Reconnaissance Systems. To Spacecraft to fulfill AIAA's request for proposal. Our mission objective is to perform a detailed geographic survey of the entirety of the Martian surface that will provide information for future missions, primarily future manned missions, to choose landing locations. We are also passport AIA request for proposal utilizing technologies that have been proven to work so that our mission will have a chance of success. Our mission constraints are that our mission must not exceed $1 billion US. This includes the cost of materials, costs of testing, costs of launching, and costs of fuel to ensure that our data will actually be helpful for future manned missions when we intend to complete all of our measurements by December 31st, 2033. And our mission should remain operational at least until the late 2030s. Odyssey is one mission that we took inspiration from, as it is in continual orbit today. It is the longest surviving operational spacecraft around a planet other than Earth. Problems. Mars Odyssey doesn't really seem to have an end of life, and with the design of the spacecraft, we're hoping that it can outlast Mars Odyssey and provide extra information to Earth past its mission date. Storms are probably the biggest hazard to our mission. The winds on Mars can pick up those small particles of dust and fling them around and create these dust storms, which impact visibility, which is going to be an issue for us since we are surveying the mission service from our satellite. These dust storms are driven basically by the same thing that drives them on Earth. The solar radiation heats up the ground, causing warm and cold air to move and create wind. Dust. These dust storms can grow significantly large to the point of obscuring the entirety of the Martian surface. These global dust storms seem to occur on an average of every 3 Martian years or 5.5 Earth years. They can completely obscure the vision of the surface, which is the storms can last from weeks to months, which is why we plan to launch as soon as possible so that the dust storm does occur, we still have enough time to take all of our data. And to launch from Earth in 2026, arrive at Mars sometime in 2027, perform a burn to slow us down and get us into Martian orbit, and from secondary wind to get us into our final orbit where we will collect data using a LiDAR, which is a laser imaging device, which will shoot a laser down the laser will back and send that LiDAR data to Earth to get a topographical of Mars.
So I'll be talking about the interplanetary trajectory. So this will deal with anything from launch to getting into the correct parking orbit that we'll be using to measure with the LiDAR. So we'll be performing a heliocentric transfer first to go from launch to reach Mars. And some considerations that we had for this was the time it'd be required to achieve and arrive and then have enough time to actually fulfill the mission. And then also the overall delta V, since having a greater delta V means more fuel, along with the time range. We decided on using the Falcon Heavy. We were originally deciding on the Falcon 9, but the payload happened to have a weight larger than what it could carry, so we used the Falcon Heavy, and it still remains one of the lowest cost for reaching Mars. So with, when we got our pork chop plot, we first looked at the overall delta V and we tried to minimize that as much as possible. But some things that made us not choose the smallest contour was actually because if you look here, you can see that you'll have a much smaller window in which you can launch. So we can't really account for, like, let's say weather, any other obstacles that we could have during launch. And on top of that, we have to basically have an arrival date that would be a bit later than the earliest possible, which, because we decided on a larger contour, we had a launch window between October 16th and November 15th of 2026, and then a arrival window between August 13th and October 13th of 2027. Our delta V's range from 6.08 to 6.23 meters per second, and we did most of our calculations using 6.23 meters per second, since that's the worst case scenario. So after we arrived to Mars, will have to transfer from a hyperbolic trajectory into a circular orbit. And we decided on a distance of 3,546.2 kilometers from Mars, or 150 kilometers from the surface. So our first delta V is going to be a retrograde maneuver, and you can see it's calculated using the speed at the hyperbolic trajectory at that desired distance that we want for our parking orbit, minus the speed that we'll have within our circular orbit. And then we will be performing a plane change maneuver. So we're going to be doing this for getting into the right plane. So it's the most efficient and able to capture the most data the fastest. So we'll basically be changing our plane from whatever our current orbit is into one that intersects with Mars's axis of rotation. We're assuming that we're in the equatorial plane, since we don't know the exact plane that we're in due to us using patch conics, but we also took under consideration the maximum inclination angle that we could have, which is 24.9 degrees. And then the calculations performed there, we got a delta V of 1.5 kilometers per second. So our largest delta V is going to be in the retrograde maneuver.
Once we went to the ground tracks, we basically used the angular velocity in the latitude direction, which is our speed from the satellite, and the angular velocity in the longitudinal direction, which is the speed of the planet itself rotating about its axis. And by using this, we could find that our satellite would be orbiting around Mars around 14 times a day. Because of this, we can see now the ground tracks. Our mission of 75%, covering 75%, will be covered way before the 2-year mark.
Okay, so I'm going to be going over the propulsion systems for our mission. We'll be using two types of propulsion system. So the chemical one for the maneuver to lower the orbit, as well as the plane change, because it has a high thrust impulse and it's able to do rapid movements. But we're also going to be using electrical propulsion to make small adjustments throughout the mission after the satellite is in the parking orbit. So for the chemical thruster, we compared the RL10C1, the Merlin 1G, and the AJ10 in terms of thrust, its maximum thrust, mass, cost, and specific impulse. And we were able to determine that for the purpose of our mission and the delta V's that were determined previously, the RL10C1 would be the best option. For the electrical iron thruster, we compared the NXT, the N-Star, and the B3, also in the same parameters as the previous one, and we were able to conclude that for those small adjustments, the NXT would be more viable. Since we're using the RL10C, it uses bipropellant, the bipropellant system. So it uses hydrogen and oxygen. So knowing the mass of the satellite without the fuel, as well as the delta V required and the specific impulse that it is able to provide, we were able to calculate the mass of the propellant, and then from there we could determine the mass for both the hydrogen and the oxygen. For the next C, it uses xenon as the propellant, and we compared to other uses of this thruster, and we were able to determine that a mass of 20 kilograms would be enough for the length of our mission. From there, we were able to calculate the propellant size tanks that we're going to be using, and they will be described further in the next section.
Now for the structural configuration, we ended up choosing a skin stringer configuration due to its, it allowed us to have the maximum possible spacing inside, as well as it has the best capabilities structurally talking. We chose it to be a magnesium alloy due to its low density and high stiffness capabilities when compared to other materials like aluminum. Now, when going back to the configuration for thrusters and propellant, we chose to have 3 tanks, as said before. These 3 tanks, the biggest one will be the one on the bottom, which is the liquid hydrogen tank, and then the other two, the smallest sphere, it's basically a liquid oxygen tank, and the big sphere, it's the xenon tank. All three are made of carbon fiber with a thickness of around 5 millimeters. And then for the thrusters, the main thruster was located at the bottom of the satellite, and the two ion thrusters were both located at special points, which it's right in between the connection between the hoop frame and the stringer to have a better overall performance. Now, when talking about the nuclear reactor or the crusty, this reactor has a mass very high for the radioactive mass, and that offsets our weight, our center of mass, to around a third of the total height of the reactor. Because of this, we created a beam in between the stringers that would connect at that exact point to avoid any torsional stresses. And this also allowed us to have a better overall or easier connection to the radiator after this. And to further on this, we're going to use pane graphite felt sheet to insulate this reactor from the overall frame. Now, for the thermal configuration, as I said before, we're going to use the pane graphite felt to insulate the reactor itself. We're also going to use some ceramic tape. Then ceramic spacers are going to be used between the actual radiator that's going to be connected to both the crusty and the two ion thrusters. Also, we're going to have a second radiator that's going to be attached to the bottom of the satellite. This radiator is going to be only for the RL10C, and it's only to avoid heat conduction to the main frame. Both of them are going to be made out of aluminum due to its good thermal dissipation, low absorptivity, and low density. Finally, we have the final configuration, which has the Atlas lighter on the top. And this is going to be, as said before, used to do all the mapping that we need, and the antenna used to communicate that information back to Earth. This is the overall configuration.
Next, we're going to talk about the fastening of magnetic systems. First of all is the LiDAR, which, as we said before, is the main measurement tool. And as such, we wanted to make sure that the LiDAR not shift at all during flight or any movements that the satellite might have. For that reason, we decided to lower the LiDAR to the frame shown here, rather than help prevent any shifting, because any shifting can cause the laser to shoot at a different angle than we might be expecting, and data that we collected. Next, the antenna will also be welded for much the same reasons, to ensure consistent communication to the satellite. Also, the large surface area through which will be welded and chosen to bolt or something else might have to use a large amount of bolts, which would create stress concentrations. The thruster, both the ion thrusters and the thruster, will both be welded to the side of the satellite. This allows for the thrust to more easily on the satellite instead of having to travel through, say, a bolt or a rivet connecting them, or again to avoid stress concentrations. Crusty, because of the large amount of heat it passes, will not be welded, but instead this will be welded onto the surface of the crusty, and then ceramic bits will be driven through the circular frame and into a nut, which is welded onto the crusty. This is to ensure that there is minimal heat transfer between the crusty and the frame of the satellite. Directly welded to the crusty for the same reason, but in reverse, to ensure maximum heat transfer from the crusty to the radiator, so that the radiator can do its job. The radiator, in order to stay in its position, not only will it be welded to the crusty, but small ceramic spacers will be between it and the frame and bolted through with, again, a ceramic bolt to ensure that the heat transfer does not go into the frame. The fuel tanks will be attached to the frame using a 941 graphite adhesive. To further prevent any tank movement, not just to rely on the adhesive, so fiber around the frame and the tank itself to make sure it holds in place. And finally, the satellite skin will be attached to the satellite frame using rivets. This is basically just to prevent sunlight and debris from entering the interior of the satellite. And the rivets are basically just a hand way of doing that without having to use weld or anything else, which is used extensively in the aerospace industry.
So for structural analysis, we'll be talking about mainly the stresses conducted during the burns. So the satellite undergoes the highest stresses during the burn maneuvers. We'll be focusing on both of them, but particularly the first one, since that happens to have a larger delta V. And we'll be focusing on the supporting beams attached to the thruster, since they're the part of the structure that's closest to the thruster. They'll probably be the ones that will endure the most stress. We'll also be thinking about progressive failure. So from the first beam or from the first burn to the second burn, anything such as deformation that could cause new stresses to be introduced during the second burn.
So one really critical location is on the supporting beams. This is exactly where the thruster attaches to the frame. So right there we have a force going upward, and the rest of the frame is considered rigid. And if that's done, you will have transverse shear at some point in the section, and also you'll have bending stress. At the same time, we're not sure how the sectional geometry will behave. So to put some rough bound into the stress matrix, we put in both bending stress and the shear stress. And after that's done, and trust is applied, we'll see that it is below the yield strength of the material if you iterate over T. And we found a thickness of the section to be 0.0108 meters. Additionally, there could be a problem of fatiguing in those beams. If those beams were deformed too much, they would go up and touch some stuff above, which are the tanks, which could cause catastrophic failure. And during smooth burns, thrusters typically vary within 5% of nominal force. There's some bounded variation in the force. At the same time, I have to assume that the frequency is constant to do this analysis and to see if infant fatigue life can be achieved. And carrying this out, I do get infant fatigue life, and a factor of safety of 1.12 is reached if this is done. And this is the lowest safety factor of the structure.
So we'll also be thinking about the deflections of the supporting beams. So if you look here, you can actually see that the distance between that and the hydrogen tank is quite small. So if there is a deflection that's great enough, it could introduce a new stress onto the hydrogen tank. And we'll be calculating this by assuming that the beams over at the end are going to be cantilevered and that there will be a max deflection during the burn maneuver. So for here, we're assuming it's going to be the max deflection. So here we did the calculation. So as you can see, we basically assume that all four of these are cantilevered beams. And so in order to calculate, we basically assumed that a fourth of what the force that is created by the thruster is acting on this cantilevered beam. And we assumed it's distributed because we had no way of calculating how the force is acting specifically on the beam. So we assumed that. And then we calculated by finding the location that would be acting if it were a point force. And then we found that the maximum value would be 0.83 centimeters, which is less than the distance that we have between our hydrogen tank and beams. So we'll be able to account for that. So also we were thinking about buckling, because if the structure buckles, not only will there be stresses introduced onto the skin that could cause it to be pulled apart, but on top of that, your hydrogen tank, it becomes more susceptible to stresses as well, because this whole entire circular frame moves closer to it, and so the beams as well. So here we did the buckling calculations. So the way we did this is we took this area and we took the normal stress that we had previously found and found the load that would be created by the thrust. We then found P critical by taking the critical load of the four stringers, which were found using the moment of inertia found through parallel axis theorem. And then we found P critical for the skin that's acting on the outside. From that, we found a factor of safety of 3.06 and a margin of safety of 1.04.
So next we're going to talk about the power consumption. So in order to determine what power source to use, we looked at the consumption from each of our systems and determined what minimum we would need. So based on that, we calculated about 1,400 watts would be consumed. And using that, we decided to compare the different types of power sources. So the three that we were comparing were solar power, batteries, and RTGs. And the main disadvantages of solar power that we found were its distance from the sun, deployment of the panels, and just the limited power output. For batteries, we addressed the shorter lifespans and degradation over time, as well as the added weight to spacecraft. And then for the RTGs, they were expensive, they required cooling, and they didn't have the best conversion efficiency. But we did determine that the RTGs were the best suited for our mission, so that's what we ended up going with. For the power system configuration and sizing, so we are using the crusty power system, and using the heat transferred from the reactor core, we generate electricity from with the Stirling engine, and using a PCU, that electrical output is filtered. And then the generator height we found was 2,328.69 millimeters, and the diameter varies, but at its largest diameter, it's 1,165 millimeters. And then for the power management and distribution, we do have a modular power distribution unit, and that's separated into three components. So the first component is the power electronics and building blocks. The second portion is the modular converters and switchgear, and the last part is the modular systems. And using additional testing to verify, we plan on using a multiple ring bus distribution system to distribute the power throughout the systems in the throughout our satellite.
So for thermal systems, there are several main considerations. Of course, the thermonuclear generator itself, solar background radiation, propulsion, both the thrusters, and then the lighter. So the crusty is the main source of rejected power, and it generates approximately 10 kilowatts of power that needs to be removed from the system. So the simplest solution is to insulate the reactor from the inside and to then attach onto directly the radiator, which will radiate out that heat. And this radiator was sized by using the formula below, and it's saying that all the heat flux is being converted and radiated out. And of course, there's some conduction going on, but that's assumed to be sufficiently insulated by the pan graphite. And using this, we found an area of 36.87 meters squared. Additionally, another consideration is the solar radiation. So there is some irradiance from the sun, and to shield the system, it's easiest to put graphite or gold foil on the top onto the hole. And the worst case is when the sun is shining in a way that most of the rays, maximum amount of the rays, is normal to the hole. And at the same time, the hole is curved, so you can correct for that curvature, since not all the power would be going directly into the hole. And doing this, you would get a Q of approximately 2.7 kilowatts. At the same time, this issue can be investigated later with the propulsion system in tandem, because there may be additional need for active systems. So the issue with the thrusters is that they do not give a constant heat flux, and that their temperature ranges are almost never itemized. So the patched solution right now is to take a heating plate onto the back and say that this will be conducting away necessary heat, but at the same time testing needs to be done to determine a suitable cooling system. And this can be integrated with the solar issue later. Ion thrusters, since they're directly on the radiator or touching them, they can be assumed to be conducting into the radiator, and they can be addressed similarly to the crusty. This makes the total area to be 41.3 meters squared. And the final system is a LiDAR system. And the LiDAR on its own has a built-in thermal control system, which operates in roughly space temperatures on the radiator side. So no additional consideration needs to be made there.
The total mass of the satellite can be split into 5 main categories, being the instruments weighing up to 900 kilograms, the tanks and fuel, with the tanks weighing 400 and the fuel 4,000. The structures of it, so all the frames, all the skin and everything, weighs up to 1.1 thousand kilograms, and all of the thermal control that was mentioned in the last section would be around 160 kilograms, and we estimated the fastening, including the tapes and rivets and bolts, to add up to 3 kilograms, with a total of 6.7 thousand kilograms.
For the cost, we have it broken down by component, which you can see here, and it totaled to around $54.4 million. For the non-component costs, we have the launch systems, the launch facility, and the ground crew, and that was estimated to be around 260 million. And then we have a complete cost breakdown with the components, non-components, as well as testing and manufacturing. And for testing, we allotted 50 million to that, and for manufacturing, we allotted 100 million. So it came out to a total of $464,412,000. And that concludes our presentation. Thank you.
Yeah.
Yes, too dark.
Does anyone have any questions?
On Zoom.
If you guys go to your mask slide,
Yes.
And
Oh, Zoom first? Okay.
anyone
Anyone on Zoom, do you have any questions?
Yeah, I've got a few. I don't want to step on somebody else if they've got some, but I've got a few.
Oh, it's okay. You can go ahead.
Okay. So at the very beginning, when you were talking about your delta V requirements, I apologize. Your slide numbers seem to be behind a little like black and gray square, so I'm not clear.
Oh.
I assume there's slide numbers in the bottom left, and I just can't see them. So
we don't have.
Go faster.
I don't know why it's doing that.
yeah.
You might want to just exit it and just click it
Really?
through.
Yeah, it's like,
Yeah.
Yeah.
Like in here?
Yeah, just get it done.
Yeah, it was somewhere in the first like 4 or 5 slides, probably.
No, it's probably the con-ups. Not sure.
Yeah. Is it this one?
No, it was just a text slide, I believe. Somewhere where you'd mentioned like
Yeah.
6 meters per second delta V. Yeah, here.
Oh, yeah. This only thing?
Yeah.
okay.
When you're talking about your range at delta V, are the units on that right? Are we talking about like the difference in meters per second of delta V?
Yeah, it was supposed to be kilometers per second.
Okay, I thought that might be the case. So check your units, and as you're talking through the presentation, right, that should raise a red flag for you, just like it raised a red flag for me. Like, oh yeah, there's something wrong here, and if you need to correct it on the fly, then do that. I think maybe on the next slide when you're talking about the inclination of the orbits. Yeah. Okay. So here we're talking about you're assuming a maximum inclination angle of 24.9. That's the inclination of the orbit that you're arriving at Mars in.
That's the plane change maneuver that we want to make. We assume that because we want to get into.
So basically the 24.9, it's the inclination of Mars that it has over the equatorial plane for Mars specifically.
Yeah, so just like Earth is tilted 23 whatever
Exactly.
degrees, Mars
Exactly.
is
So
24.9. Okay.
yes.
So you're coming in more or less on the ecliptic.
Yeah.
And so you're assuming that you're in the ecliptic and that you're entering at basically in the ecliptic at like 24.9 degrees relative to Mars's equator.
Basically.
Okay. Could you be somewhat out of the ecliptic? I mean, it seems like, you know, from the perspective of the ecliptic plane, you don't have to be very far out of it to like come into Mars basically on a polar orbit trajectory, right? Like you have to be, you know, 0.0001 degrees out of inclined relative to the ecliptic, and then you're, you know, shooting over the pole of Mars, right? So I'm not super familiar with you know, the realities of orbital mechanics, but it seems like you could maybe be coming in at an inclination angle more than that. And if you're telling me you want to come in at a polar angle, you know, maybe
Well,
that's beneficial to you.
That's the angle at which we will be basically arriving. After that, we do the plane change maneuver, and that should basically bring us to the polar trajectory, basically.
So you're saying, well, I mean, if you're talking about getting to a polar orbit from that, you're talking about doing an inclination change of what, 65 degrees?
About
So if you come in at a smaller inclination angle, would you maybe have to do a larger plane change?
To do it, coming in from the equator would be the highest angle of the plane change, since
Yeah.
if it's not there.
Yeah, and you wouldn't have to be very far out of you know, the ecliptic plane to come in basically on an equatorial plane or around Mars. So that I guess that's what I'm getting at. Maybe is that if you're talking about doing a conservative analysis, then I don't
well,
think we ought to be
for
using
that.
the 24.9 degrees.
We were for that by doing more than the 75% that was required, even if we're losing a couple degrees, due to the shape of the planet itself, we'll still be covering more than 75%, even if we're not all the way to so basically if we arrive at 0 instead of 24.9, we will still be covering more than 75%.
Yeah. Okay. Let's see. When you're talking about your subsystems, how you're attaching them to the vehicle, it seemed like most of them were being welded, and it sounded like you were doing that so that you had precise locations on things. My experience is that subsystems tend to be fastened and not welded, and there are a lot of reasons for that. One of which is that you're going to go test this, and inevitably something is not going to work when you test it. It's going to have to be swapped out, and if it's welded in, that is a major process compared to something that's bolted in. So I'm suggesting, I think, that you figure out a way to locate it precisely and still use fasteners. I don't, you know, it might be that comparable systems have decided that welding is the way to go, and that's the case. But it certainly introduces complications.
Sure, that's how like for me specifically, because we're dealing with fasteners, not only is it a little stress concentration more so than so we're unsure about stresses if it would
Yeah,
cause.
I certainly
Yeah.
recognize that, and that's you know, certainly an issue. However, for subsystems like this, I you know, I think it's probably feasible to manage those. And the other thing you have to think about with welding is I assume you're using aluminum structure here.
For the light bulb and the I'm pretty sure.
Yeah. So if it's aluminum, as soon as you weld aluminum, you're gonna lose your temper, right? And not in a get mad sense, but in a material temper sense. So that means you're going to weld it, and to get the properties that you think you're going to have, you're going to go reheat treat it. which adds time, cost, and general hassle. So not to say that that's never the right solution or that it's not the right solution in this specific instance, but it certainly raises complications. So be aware of those.
Just for the other ones, to keep them in place, but for other ones, like for the crusty, just to maximize the heat transfer.
I'm sorry, I had a little trouble hearing you. You're breaking up.
If you look to the, because I understand what you're saying for the live and the antenna. Some of the robots, like for the to the crusty, which was mainly not necessarily to kind of fasten it in place, but also just to make sure there's the most heat transfer from the crusty to the radiator.
Yeah, and I'll tell you that I'm not familiar with using ceramic bolts. That's pretty exotic to me. I believe it can be done. It certainly makes sense, the type of application you want to use, but it's not something I'm familiar with, so I'm not going to really speak one way or the other on that.
Assuming that basically, to be the most conservative we could, we were assuming the maximum heat that the cluster would produce would go into the regulator and then turn the bolts. So we wanted a bolt that would stand really low temperatures, and the ceramic bolts were the only ones we could find. And from what we could tell from online sources is that the tensile strength of the bolts themselves should be enough to deal with any stresses. So we figured it would be it's a real choice, but it was kind of the only choice we had for the heat transfer.
I frankly, I wouldn't be so concerned about the strength of the bolts, but more so about fracture of the bolts. Ceramic tends to be brittle, and if there's some small crack in there, you put it under tensile load, and all of a sudden, it's potentially going to propagate. So, but again, it's kind of an exotic application to me, and I'm not that familiar with it, so I'm not going to say that it can't be done. When we're talking about the stress analysis, I think you were talking about the main critical load for your system was like thrusting from your engine.
Yes. So we basically did our failure analysis during the two burns, and we focused mainly on the first burn since that would be where our beams would be enduring the most stress.
Okay. I'm curious, did you consider the launch environments on your system?
No, because we didn't know how much the vibrations and stuff would be for launch.
Okay.
We're
I would
assuming that
expect,
we'd find that through testing.
yeah, I would expect that that's probably going to size a lot of the structure in your system. The launch environments, if you're launching on something like a Falcon rocket or something, you've got significant G loading as like static load and dynamic load going on. So definitely consider that. But so given what we did, when you're presenting a stress analysis like this, I'm a simple guy and I like to see pictures. So definitely show me a picture of what you're analyzing, the load that's on it, and you're doing a beam analysis, right? MC over I, VQ over IT. So I want to see a picture of the cross section of the beam. And then so we got that kind of on the next slide. So on slide 37 here. And looking at this picture, like from a structure standpoint, this is like a super structurally inefficient way to attach your engine. I'd like to see some sort of angled support in there, so you're not trying to take all that load through a flat plate and like beam it out through a not very stiff connection to the outer structure of your satellite. Do you have room in there at the back end to like put a triangulating diagonal piece between like the rim of that inner donut hole and the outer rim of the satellite?
Yeah, we have quite a bit of room because of the gas tank. Basically, the shape is kind of like a dome. So, I mean, we can go. I don't know if we can go all the way to the base, but we can definitely get closer to it.
Yeah, anything you can do to stiffen that up would probably be to your benefit. I think you said you had like 3 centimeters of deflection of the engine.
Um, 3 centimeter deflection, that's like a over approximation because we assumed it'd be a free end cantilevered beam. And that was just to decide how far our hydrogen tank would have to be from the beam. So we do have a little bit of space there as well.
Yeah. So I mean, that's a lot of deflection. You know, when we're talking about structures like this, that's significant. So I think if you can minimize that by stiffening that structure, you'd be doing well. Can I ask what's the cross section of the beams? Are they like solid, like square rod? Are they tube, or what are they?
They're not solid and they're not rods. They're square cross sections.
So like square tube?
Yes.
For which ones?
For all.
Yes.
Okay, so that's good. That's kind of, you know, maximizing the stiffness for the amount of weight. Again, if you can't do anything else, I would say, you know, make those rectangular, right? They probably need to be taller than they are wide, so that they add that that flexural rigidity in kind of, you know, the motion of the engine actually along the satellite. So if you can double the height, you'll get 8 times the stiffness, right? Because it goes with height cubed. So I would definitely look into doing something like that to kind of optimize the cross section there. Let's see. The other impact from, you know, having 2 or 3 inches or 2 or 3 centimeters of deflection of your engine, right? Everything that's connected to your engine, especially things like fuel, are going to have that much compliance in the system somewhere, right? So that they can flex as the engine moves. So that large deflection complicates things. When you're doing the buckling analysis, right? So you're talking about like the load of the engine kind of compressing against the inertial mass of the satellite, and looking at like buckling of the skin structure.
Yes.
Yeah, so I like that you're considering buckling. Space structures tend to fail in buckling, so that it's good that you're thinking along those lines. From what I can tell from your structure, it looks like the load is mainly going to be directed into the red bits, right? Those are like stringers running axially along the length of the satellite. So I would say maybe accounting for the skin is maybe optimistic. I don't know that you're going to get the benefit of that much skin. I would look at buckling of those stringers kind of independently.
Okay.
And then, I think that's probably a more realistic approach to it. The skin itself, what were you considering for the buckling of the skin? Was it basically like buckling of a cylindrical tube, doing like oiler buckling of a long tube?
Yes. So we considered that because we have rivets that attach from the like stringer structure to the skin.
Mhm.
But we can just consider the stringers itself.
Yeah. So what I would say to that is your skin is going to behave somewhere between like a tube buckling in like oiler buckling and flat sheet buckling. And there's a lot of good like NASA documentation about how curved stiffened structures buckle. It's probably overkill for a capstone design project like this. I think you've done, again, probably a lot of good structures work here, and probably more that you aren't showing. But be aware that you can go find a lot of data on how structures like this are going to buckle, and it's not as simple as just saying, okay, I've got oiler buckling column where I'm looking at a load acting on a cross section of a tube, right? It's the buckling modes are going to be significantly more complicated. So, but I think if you sort of idealize it and say all the load is going to be able to be carried by the stringers, then that's a conservative thing and you know a good way to say we don't care what happens to the skin. It can buckle and we're not relying on it to carry load. So. But again, I like that you're thinking along the lines of buckling. I think that's something that a lot of teams overlook in projects like this.
So
When you
one of the biggest pros of avoiding the buckling for the skin, it's mostly to avoid it touching and the main radiator and increase the heat conduction through there. But I mean, we could still get rid of that anyway.
what is your skin touching?
So, I mean, as you can see here, there's like a bigger circle outside, that's the radiator. So if the skin buckles in any sort of way and it ends up touching the skin, it'll dissipate some heat conduction into it. Like you're gonna have some heat going into the frame, which we want to avoid.
Okay, yeah, I would say if it's so you're relying on it to like have a standoff from anything internally.
Basically.
Okay, yeah, so that becomes a more complicated analysis if you need to rely on it not deflecting. So yeah, again, it's something that is significantly advanced like structures kind of stuff. So I'll just leave it at that. I love that you're thinking along those lines, and there's probably a lot. You know, if this project were to go forward, there's a lot more to do along those lines. But you're thinking along them, so I like that. On the you'd mentioned that you were gonna like electroplate gold foil to the skin of your satellite.
Yes.
Is that typical in these types of vehicles?
So it has been done, and usually the standard is to use multi-layer insulation, but at the same time, you want to conduct out the heat that's generated by the crusty in case there's some problem with like the pan graphite felt. And if I use that, then I'd be insulating inside all the heat, and it could cause heat buildup.
Okay, so you're kind of relying on the fact that you're conducting heat out through the skin, but we just talked about your skin's not touching anything. So I guess I'm a little confused.
No, so it's electroplated to the hole, but its purpose is only to reflect the solar radiation. Like it's not connecting or bridging the radiator and the frame and the skin.
Okay. Yeah, I'm just wondering because again, I'm not super familiar with how this is done, but I almost think that bonding it to the skin means that it's going to conduct heat into the satellite, maybe that it's absorbing from the sun.
So you're thinking it's
rather
more
than having.
Oh, I see.
Yeah, rather than like heating, if there was like a vacuum gap between it, right, and it was only sort of touching it at discrete points, then the insulation is going to heat up and radiate more effectively. And if you're bonding, then everything's going to heat up, and maybe it still radiates as effectively. But yeah, that seems odd to me. But again, this is not something I have a ton of experience with, so I'm not going to say one way or the other is the right way to do it. Let's see. And then you had a slide where breaking down the mass by system. Yeah, here we go. That's a lot of structural mass and not very much fastening mass. Again, you're talking about rivets to hold the skin on and welding everything else. I think when by the time you talk about, even if you do that, by the time you talk about like fastening all the, the power subsystems and the communication subsystems and everything in place, I think you'll have significantly more fastener mass relative to your structural mass. So yeah, I think you're undercounting there. But what's your mass budget, by the way?
Our mass budget,
I think
it would be the maximum that
Our total budget, it's what is it, less than 500 million, so we still have like half 500 million left to.
No, I'm sorry, mass budget.
Come on,
What,
mass.
how much mass did you, were you targeting?
Oh,
It's the most that Falcon Heavy can carry, which is
It's on the slide.
okay. It's up to 4,000 kilograms.
And what were you on the previous slide? So you're 60-70% above your mass
I'm
budget.
pretty sure I wrote the wrong thing. I wrote it for Falcon 9 not for Falcon Heavy.
Okay, definitely figure that out, because if you get a shed, 40% of your weight, that's a big haircut, right?
16,000. It shouldn't be 4,000. It should be 16,000.
Yeah, we
Okay.
went back and forth between Falcon 9 and Falcon Heavy quite a few times, so probably that was one that we missed.
Okay, yeah, that's definitely something to keep very good track of, and I'll say anywhere in whether it's aviation or space, mass only grows as your systems become more mature. So expect whatever number you have at this stage to go up. And it's probably pretty typical to have, just like you have a management reserve in budget, you have a management reserve in mass, and say, we expect that we're going to grow by 10-15% on our mass, and so make sure that wherever we're at in our initial design, we're 15% below our maximum, right? Whatever the mission maximum is that says above this, and we don't have a vehicle, or we can't launch to Mars, or whatever the constraint is. Give yourself like 15% of that, and track it throughout the life of the program.
Just to answer what you initially asked, the reason I think our structure elements is so much more than the fastening is because obviously the fastening would go up if, like you said, we changed to bolt, the fastening makes us so large because most of the stuff is currently just welded.
Yeah, but even then, right? There's stuff that we talked about, like the LiDAR systems, and we talked about the antenna stuff. But you're going to have various power things. You're going to have hardware that like computing hardware. There's going to be all sorts of stuff that you're bolting in place inside. Hope that you're bolting in place inside your satellite. And so I think you're undercounting your fasteners a little bit. Probably a lot.
Even if that's the fact, though, we overestimated the amount of fuel we needed anyway. So, we can still, because we were planning on staying even more than the amount of time in the mission is, just in case we want to keep using it. So even if I think we overestimated by, what was it, half a ton around. So we have a lot of wiggle room with that.
Okay. Yeah. Again, just make sure you're accounting for things appropriately. I think that if you're breaking things down like this, it's important to be realistic where you can and conservative where you can.
Any other questions?
Not from me. Actually, I gotta run, guys. So I'm not gonna stick around for everybody else's questions. But I'll say good job and go Gators.
Thank you.
Thank you.
Any question?
Yeah, do you guys not have pressure in tanks?
No, we do have them.
You do have them, where are they?
So just show this one. Yeah, we have them here.
Well, aren't those your main tanks for your Xenon, your H2?
Or do you mean intermediate tanks?
So for the bipropellant, it has to be pressure fed so we don't get backflow through the engine and like blow up our pressure tanks, right? So that we ensure flow is going in. So either are you pressurizing your main tanks to a very high bar, or are you using like pressuring tanks to pressurize it as fuel goes down?
I guess as the design stands, it doesn't have them, but
We really took into account what SpaceX is doing with their carbon fiber, their 12-meter carbon fiber ones. And we just overestimated the amount. So they're using a 4 millimeter thickness. So we overestimated and used the 5 millimeter thickness for it.
Yeah, I'm asking how we ensure that we have positive pressure flow to the engine. So as you burn through your fuel, that pressure in there, even if you can pressurize it high with the carbon fiber tanks, which are newer and lightweight, as you burn through all of your fuel, that pressure is going to get lower and lower and lower, to where you might not have your pumps able to circulate your like your propellants to the engine.
I think
There's definitely something we should probably consider when we go back to fix some things. So yeah, thanks for the information.
Any other questions?
I got one. You guys were talking about that one of your considerations against using solar was the deployment of the panels. But then you were talking about the deployment of a radiator. How does your radiator system work?
The radiator is not deployed, it's already part of the structure itself.
So it'll always be.
It would always be
radiating
like that,
heat,
yes.
But then during your peak heating condition, would it be then absorbing more heat from the
Uh,
sun?
it,
or
it
how-
wouldn't matter. Well, first of all, it's made out of aluminum, so it already reflects like 97%. That's why it's so good, and we are not plating that part with gold. But other than that, the radiator area itself, it's already way bigger than the needed one. So the area, the needed one, I think it was like 42 meters squared. It's around 70, so it's almost double.
So with all of that additional mass for the radiator, plus all of the additional mass for what the reactor was called, crusty. For the crusty, how did you guys weigh the comparison of the mass versus power consumption? Because a majority of your power consumption wasn't it going towards removing heat from the system, or do I have that wrong?
So yeah, most of the power goes to the next C thrusters. They're used at the minimum possible power they can use. But we do need a constant power supply for the LiDAR, and it needs to be stable. It cannot wiggle. That's why we ended up choosing the reactor instead of solar, because if we're on the other side where we are not receiving sunlight, we don't want to have those issues with lower peaks.
Yeah, I was just wondering that with such a low watt consumption, why, like, how did you guys weigh your decision matrix to go with nuclear? Because nuclear typically generates a lot of power for what we see is very expensive and very heavy. What specifically made you go with nuclear instead of just solar and batteries?
So the nuclear we used, there's 10 kilowatts generated, but out of that, I think it's about 3 kilowatts that are usable for our things. So we decided on that because that would work best for being able to maintain the power for everything. We basically assumed if we had to use everything, including like the lighter and the thrusters all at once, that it would be able to meet that threshold. And since the amount of output is slightly greater than our power consumption, we don't need an external source to store that power.
Also, we're going to be too low in the atmosphere, so we don't want to have to deal with any solar radiation bring us down, basically.
Like force.
Yes, basically.
Where are you guys orbiting at?
100.
Should be
Right before.
higher. Right before.
Yeah. Yeah, that's from the center. It's 150 kilometers from the surface.
Did you determine that to be where you're going to be getting significant effects from the atmosphere, and that's why you?
That's exactly where we're gonna avoid any kind of dust storm, and the closest we are, the better resolution we're gonna get with the laser. So that's like the best threshold we could find to actually go to
So that's
choose
why
that.
solar wasn't an option. But what does Krusty stand for?
I think that's an inside joke of NASA, but it breaks down this kind of.
NASA programs that make that.
I don't think it stands for anything.
Okay, that's not what you guys think.
Sure if it was named that.
You can find other ones by searching kilopower
Yeah.
reactors, and that's the only one that is actually being like constantly tested and used.
Yeah, we were able to find a constant temperature. So they tested it at the, if they were using the highest amount of power or the lowest amount, and it roughly came out to 800 Celsius, if I remember correctly. Yeah, 800 Celsius. So since we're actually going to be always using less even in our max conditions, we assumed for our temperature stuff and like our insulation, it'd be based on that. So we were able to, because since it's still something relatively new, it's hard to find like temperature conditions when it's operating. And this one had thorough documentation on that.
Oh, could you go to your propulsion selection slide? Just going through the engines, I think that first one. Yeah, the thrust was just in pounds. Instead of newtons. Sorry, we had the same engine, so the numbers seemed a little weird at
Yeah.
first. I think that's all of my questions.
It's a good engine.
It's good.
You guys have enough questions? No.
Could you go to one of your CAD models? Oh,
Sorry,
It would-
to give you the
When you
microphone.
go to
Just one with the ion thrusters, and I guess the general question is, what sort of like functionality do those ion thrusters provide for you guys?
They're mainly for like perturbations or other things.
And then why
Like
did you
supplemental.
decide to just do two of them along one of the diagonals and not four?
Well, they are not like they're offset from the middle, so we thought that with two, we could rotate it as we need and use it as we need.
And you think two would be able to provide you enough thrust to overcome whatever perturbations you have, even if you're pretty close to the top of the atmosphere?
Our assumption is that, right, like where we're orbiting should be basically the closest we can be to have basically no atmosphere. So basically the only perturbations we're worrying about is like almost kind of just primarily gravitational effects.
Okay.
So it should be able to.
And they're already pretty small, so.
Yeah.
The perturbations were like on a lot of magnitudes smaller than the like Mars itself. So like it was basically, so those were just like supplemental, as I said.
Awesome.
I think you had a question. Did you have a question?
No.
Oh, I thought you did. Okay, so. No,
Yes.
last chance. Okay, so great job. I think the presentation is really great, and also the slides, everything. Just like some, where they already covered. They had great Tom and students from a group and the LTA. We all had great questions, so they already covered most of the important points. I just have really some small places that you may consider if you want to do anything, in your report. So the first one is the thruster selection. Let's say since let's give some chance for you guys to talk. So because I feel like you guys really didn't talk for the whole presentation and Q&A. So the first one is that your thrust, they're really in different order magnitudes. And I feel like you are choosing the thruster there, the general thruster really in different order magnitude. I would say that what is your expectation before you choosing this one for the thrust?
Well, I would say, I mean, the specific impulse obviously is like optimal in this regard.
Let's focus on thrust. So for the thrust part, since there are like so much difference in these three options, I mean, probably I want to know like, what is your expectation of the thrust you want your thrust to have?
So a lot of time, I don't know, I'm not expert in this like propulsion system, but I feel like it's not really, I mean, the mass is lower the better, cost is lower the better. But for the thrust, is it really that the higher the better, or it's like they're really in different order of magnitude? I mean, there should.
I guess the reasoning there was that we didn't necessarily need as much thrust. I know they provided, like the other engines provided like a higher thrust.
Based on the scores, is like 9,000 is 1, 23,000 is 8, and then you have 220. It's basically is 10. So basically, I guess your way to score these 3 is the higher the better.
So
We could have considered something in between, but based on data we got and.
It's not something in between, because let's say for the propulsion system, you have the delta V for each stage, and you have like I guess in the trajectory design, you probably should have some expectation like what kind of thrust level that you want. If that makes sense or not, I'm not sure if I explained this question like clear enough. Because I see so much difference in the thrust you can generate from the 3 options. There should be like the best one that can match your expectation. So I want to know if really the higher the better, or you have your own expectation to a certain order magnitude.
Yeah, I guess that's something that we're gonna have to reconsider when we're doing the trade study for this again. What scale like it falls underneath for like, I know because that is a little confusing when we're in terms of like grading. We probably have to reconsider how we did scoring for that.
How about you guys?
yes, the main thing was that we were aiming to get a really high specific impulse. At the same time, we noticed
So you do want the higher the better.
we want high specific impulse. That's the main thing. But it's very common in all the papers to have.
You want the higher the better, but why like 220,000 is 10, but 23,000 is 8. It's 10 times higher.
I do think that like we want a high thrust, but I think like to an extent, like I think at some point it just becomes unnecessary. Like we don't actually need that.
That's what I mean. You have your expectation.
But we don't
It's
know,
not
like-
the higher the better. There's should be a optimized point that suits my expectation.
So for this one, basically what we compare is it's utilized most of the times just to get out of the atmosphere, and that's why they require that much thrust. But actually for maneuvers in space, you don't require that much. So even though it's the higher the better, there's kind of a threshold that it's not much different.
That's what I mean. So basically, when you do the trade study, I would prefer you put your expectation there first. So to achieve this mission, my expectation is thrust to a certain level, and then
During that though, would lower any other scores, it will only increase the score of the one we chose. Because if you're saying we're supposed to choose a parameter, basically this one would be the only one that goes up because it'll basically be on that threshold. But this one will stay the same because it's still over the threshold, and this one will stay the same because it's still under the threshold. So I don't understand where would be.
We should like target like a specific like optimized thrust, and then the further you get away from it.
You need to have that as, wait, are you saying so to have that as like a basis for the scoring? Like to have a reason for why the scores are given?
I'm just confused. Like you have 9,000 as 1, and you have 23 as 8, and you have 220 as 10. I'm just confused about this scoring. I mean, and I don't. Let's forget about it.
Real quick, we know that we don't want to go with something that's thrust optimized if we're talking about an upper stage. Why not just do the chemical analysis for only upper stage engines? So that you don't have that problem at all about how you weight thrust. So like you were talking about earlier, the Merlin 1D, since it's
Yeah, so
it's thrust out.
even though it's thrust optimized, they're still using it in space.
Just because they had one engine at the time.
Yes.
But you guys for that final report have the capacity to pick from, I mean, there's like 3-4 different versions of the RL10-1C alone.
Yeah, but none of them are being used. Most of them are either not being used or not being completely
There are
optimized.
upper stage specific engines that you could look at that would get you probably a more efficient trade study that didn't give you the problem where like, yeah, you have something that's thrust maximized, that's scoring higher when that's really not one of your main concerns.
So are you saying that we should group some of the,
If you know, so you have the Falcon Heavy that's getting you there already, so you're in space, so you don't need a thrust optimized engine, because thrust optimized engines, they want to put out as much power as quickly as possible, because they need to escape the sphere of influence, right? So when we're talking about the chemical thrusters, like the RL10C, it's an efficient engine and it has high thrust, but it's not thrust optimized, it's more efficiency optimized. Like if you look at the specific impulse for the two rockets, you can see how
it's
the RL10C is much more efficient. So if you like go online, you can specifically find lists of engines that were designed just for upper stages, right? So none of them are going to be thrust optimized, so you won't have that problem with the final report.
Yeah, we'll take that into account. I think we can probably redo our trade study and compare like better engines that are more comparable to what we need.
Yeah, so we actually used that one at first because we were taking into account the fact that we could use the Falcon Heavy to get us all the way to Mars. So that's the principle.
You are sticking with
Yeah.
the family.
Basically, that's why we kept that one in, because that's been like that since the beginning. Before we actually knew that we could use the Falcon Heavy to deliver us all the way to Mars.
The next one is the structure configuration.
Which ones?
Let's give you a opportunity for them to talk first. So the skin stringer configuration, you chose the magnesium alloy and because of density and stiffness.
Yeah, that's the reason.
I mean, let's look at big picture. We do structure, we chose the material for structure, and I'm just a little surprised to see that, oh, I chose this material because of density and stiffness. Oh, I mean, I just need some justification.
In terms of aluminum comparison, magnesium does prove to have better stiffness properties, and that is important for the structure of the satellite itself.
Sorry, could you please?
Compared to aluminum, he's saying that the magnesium alloy offers better. I mean, it has low density and offers better stiffness. So, like that's the reason why we.
So you consider density and stiffness is more important criteria for choosing the material for structure than, let's say, strength to weight ratio.
That's what I was going to say. It's explaining it.
You're worrying about the diffraction first, then the structure failure. Is that what I mean? Because stiffness is for calculating deflection, right? What is stiffness for? The higher stiffness, the less deflection it is. What else?
Yeah, we're right about the strength to weight ratio, and that's why we chose it over like aluminum, because it was slightly better than.
Yes, answer my question.
I'm sorry. Yeah, so we chose magnesium alloy over the aluminum because it had a better strength to weight ratio.
You put here is density and stiffness. There's nothing related to strength.
As it being I considered it like a sufficient explanation at the time, but it's like strength to weight ratio.
Yeah, it's in the next.
Remember the next line?
Can you go to the next? Yeah.
Oh, that's for the carbon
Then let's
fiber.
go back. There's nothing in the next slide.
Yeah, we should.
Anyone else want to answer this question? I mean, I'm just surprised to see that you chose a structure material because of density and stiffness.
It still has a very high weight to strength.
But if you didn't put it here, you in the presentation you talk about like I chose magnesium alloy because the density and stiffness. If you have considered strength to weight ratio, you should put it here. Right? Otherwise, when I see this, okay, density important, stiffness important. How about strength? Consider if the structure will fail or not first, then consider if the deflection exceeding some requirement.
So originally, when we made this structure, we were considering aluminum. We then checked some of the stresses, so specifically like the normal stresses and stuff. And based on that, we found that magnesium would work on our design. And then from that, we looked at density in particular because we wanted a lower density so the fuel would take up less space. And then we considered stiffness.
So you did consider the strength first.
Yes.
Yes.
That's what I said in the presentation. You need to put strength in the first. Otherwise, for me, and also in your presentation, your explanation, you clearly said I chose magnesium alloy because of density and stiffness. But now explain that you did consider strength first and then consider density and stiffness. Am I right?
Yes.
So yeah.
I think we just put that in wrong because, yeah, we did consider strength first, but then what you said was the density, since we wanted lower mass of the entire frame.
Okay. So. Stresses on supporting beam calculation. Again, let's give them some opportunity to talk first. So here, why specifically put a negative sign for the stress? For the sigma axis? I just need some explanation. I'm not saying anything is wrong or why put a negative sign? I mean, there are compressive that tensile, of course, but why specifically here put a negative sign here? I want to know a reason.
I guess that was kind of like a directional type of thing, like a nominal way that we assumed.
Direction?
Well, for the stress, like we just assumed that the thruster would cause a bending in a certain direction. So I mean, I don't know. So if we're using the frame of the satellite as like a reference, then
To answer my question. My question was the negative sign. What's a negative?
Compression, and that's why.
Compression?
Yeah, for the.
But we're not using positive value.
Yeah, we should use the magnitude for.
I'm not saying that you should use, I just need some explanation why use negative value.
Yeah, it's just a beat bending sign convention for.
Sign convention?
Yeah. Like.
What do you mean by sign convention in bending?
Yeah, typically like tension is reported positive, compression is negative for sign convention.
Yeah, I know that.
Yeah, but
My question is why put negative sign here? I know positive is tensile, negative compression, of course, I know that.
why? Could be an error.
On the next slide. This is gonna be pushing up here.
Okay,
And if you're considering the top of this beam, and I guess I should have had a diagram, like you take a section like this. And I'm looking at this point, you'll have compressive stress there. And if I'm using the compressive yield strength of the material. And I put all these values to the stress matrix, it's only then I can evaluate it.
okay, how about, well, this compressive side, there's a tensile side, and this side is stress for tensile is lower than compressive.
That's what I was.
You know what I mean?
Oh,
They can suffer from higher compressive yield strength than tensile yield strength. So if you are thinking about like, well, I know that if you have bending, right? Let's say you have washing this way, and this is tensile, this is compressive, right? And let's simplify as a beam, so magnitude is the same, doesn't matter. And this one you probably will compare with compressive yield strength, and this side will compare with the tensile yield strength. And we know that for most material, tensile yield strength is lower into magnitude, lower than compressive yield strength. That makes sense?
yeah, that makes sense. It might have been. It might have been in this material that it's like special, I'm not sure exactly. I think.
What kind of special material do you use? That you think the compressive strength is
This is a magnesium alloy. Like it's,
You can Google it now. If mechanism alloy is like the compressive yield strength is lower than tensile yield strength, I don't believe so.
I think, yeah, that should be an error.
You need to give an explanation why you intentionally put a negative sign there.
If it is an error, then likely even still this second term, like this,
Can you change it back to that slide?
this second term might still make it fine, because what I did is I put into the stress matrix, not just the state of stress at the top, which should have been just the bending stress, but also this stress to sort of get like account for problems with like the sectional geometry. And I guess if we assume that the sectional geometry isn't a problem, it might still be the case that I'm still interarranging the material. But yeah, this is an error.
Sorry.
So like if I have a sectional geometry, like I'm gonna have, I will likely have higher stresses like near the edges than it is in like a round like beam.
Oh, okay. You're saying like, I have, it's on the top and bottom surface. Yes, I know that.
So that's why I did this calculation. And I guess if
Yeah, I know that you are calculating.
I see your point, Elizabeth.
Yeah.
It's likely wrong.
Okay. Okay, so, next slide. Let's give them the opportunity to talk first. So the thickness, T 0.0108. What is dimension? What for the T? What? T of what?
Sorry, can you repeat the question?
The T equal to 0.0108 meter. T represent what?
The thickness.
Thickness of what?
The tube.
Thickness of
The support beams. The support beams.
support beam.
Yeah.
It's because I heard you guys said in the previous Q&A with Tom, it's a tube, square tube, rectangular tube, right? So it's the dimension of the tube or the thickness of the material.
I'm not sure. I think
So let's say,
wouldn't be like
so let's say this is a tube. Is this dimension or this dimension? Is the thickness of the tube or this dimension?
Yeah, it's the thickness of
It's-
it will be the difference between the inside diameter and outside diameter.
So your thickness,
Yeah.
10 millimeter. Wow.
You had to go through several iterations.
Yeah, I think if we do exactly what he was saying, putting the diagonal corners, it would likely reduce them.
Okay,
Because then you'd have that smaller bending stress.
because I mean,
The tube itself,
you're saying you have 1 centimeter thick material,
the tube itself is 10 by 10
10 by 10 millimeter,
centimeters.
centimeter. Okay, it's 10 by 10 and the thickness
Yeah.
is 1.
Yeah.
Okay,
Well, that's what we were trying to say for that. Like the difference between like the inside diameter and. Yes, I see his point, but the need for this.
yeah, so consider this one.
That's why we have that much deflection, basically. And not the most significant.
Okay. And the page with 2.83 deflection calculation. First, so for the force, is the direction correct?
Say where the direction is correct because that distributed load is coming directly from the thruster itself. So it's only acting on that, like in that area, so the deflection.
Directional force.
Yeah. I would say it is.
it looks a little weird for me because based on your structure, this is a circle, okay, and you have the engine installed here. The direction should be in this direction,
Yeah.
but the one you put is in this direction. You know what I mean?
This image is like not, it's slanted, it's actually meant to be done.
Fancy because it's very clearly show that is your direction, your force direction is in this direction.
Should have put the force arrows in diagonal to show what's going.
You guys are smart. You could figure out a way to how to demonstrate direction this way.
The only problem with that was that we couldn't show the beam itself. That's why we basically showed it like that.
You think it would be better, because diagonals.
Say like drawing a circle and putting like a dot there, like kind of like in physics.
Using a side view.
To show a force that applied in this direction, you can rotate the plane in a way that, okay, now you rotate it at an angle. Now you can show the force.
But if we do it from like top, you can't tell that there's like, because we're only doing a fourth. If I did it from the top, you would just see like the circle. Like you would basically just see.
As of now, it's inclined how you're saying. That's
Yeah,
why-
It is slightly inclined, so it's confused. The force dot, like,
We look to the side, to see that like the direction going like this.
Like
way.
if we show two
But-
pictures,
But you wouldn't be
Yeah,
able to
it's like,
see
we do,
it,
yeah,
and then
section view.
the shape of the structure, like where exactly.
I'm sure there's one way to show the correct one rather than this one, because this one is very confusing. This one obviously is wrong.
so you think that, like a side
Do you-
view?
I mean, this direction shows here is wrong. You can say that you don't know how to show, but this one is wrong.
Yeah, but I guess it doesn't specify what plane it's in, so it's, yeah, I guess it is wrong then.
Yeah, because if they, let's say, if the people only see this page of the slide, they don't know your whole like analysis or structure or function of this structure or anything. They when they see this picture, they will see that okay, your force is applied this way. Makes sense or not?
but it's not completely flat. So I don't understand why it would be an issue. It's been used like this several times in several books. So that's
Let me show you a textbook.
Arrows could have been angled.
Yeah, like.
Yeah.
They could have done.
No, yeah, that's probably on our part, that it didn't adjust with the plane change that we did for this image, but.
I think it's just because the image was probably, it was.
You can say that you didn't figure out a way to show the force, but you cannot keep fighting with me that one is correct.
No, it's incorrect. It's.
So the 2.83 is the deflection.
So that was overestimated. Maybe because we assume this is a freehand, it's definitely going to be less than that because we didn't account for the circular frame. The geometry is so
Okay.
complicated.
Okay. That it's probably is the deflection at the center or the
Yeah.
deflection connecting
The center. We did the center because that was going to be the max.
Okay, okay.
We did a version with linear, but like approximation. But we just figured using that one because
So we just
That's
assume it's like a beam, then we distribute force applied in that
Yes.
section.
yes.
Yeah. After the frame will help reduce.
Yes.
If you consider the
Yeah.
frame there, because I mean, it definitely
Yeah.
will reduce the deflection.
we're just saying like worst case scenario.
Okay. One thing, I'm not saying you guys are wrong, just I mean, I'm in two presentation, one's theirs, one's yours, and then the RTGs, they say, okay, it's too expensive, do not consider, but in your power sources comparison, I think you guys chose the RTGs, right?
Yes.
So justification.
For budget leftover, so we were able to like contribute like a sizable amount to like the Krusty power generator. And also for like like the solar power and batteries, like we felt like those had a lot more downsides
Mm.
compared to like putting cost into something that's, you know, more expensive. So we kind of weigh it like that.
Okay, so make sure that you put a very clear trade study
Right.
to persuade me that RTG, yeah. And power management distribution. The figure on the right. I cannot read anything on the graph anyway, so don't put it there. For the mass estimation, did you guys consider the power system?
Yeah, it should
be
be
across
instrument.
Okay. Because normally when I think like instrument is an instrument for doing the experiment. Okay. That's all the question I have. Do you have any question? Do you guys have any question? No. Just one more question. I'm not. So for a 3 credits class, so I agree that, well, do you guys agree that it's like on average for 3 credits class, each person should spend about 12 hours per week in a 3 credits class? Makes sense or not? Right? So let's say 3 hours lecture and 9 hours working time. And for our class, well, it's designed, but I still expect you guys like have spent total 12 hours per week in this class. So I'm just curious, I'm not criticizing anybody. I just want to know, like, each of you have estimation like per week, how many hours each of you spend in this class. So start from you.
I mean, it definitely varies sometimes.
Yeah, on average.
On
don't
average,
yeah.
I guess I would say around 3. What do you think?
Yeah,
Including come to my lecture.
Like, yeah.
It doesn't mean that. Approximation. Come on.
I'd say like maybe 15-ish.
Yeah, that's what I.
15 to 20.
Yeah.
I'd say probably like 12 or something.
15, sometimes a bit more if it's like a lot of calculations or iterations.
Yes.
I'd probably say like 8 to 10.
In the lower, around 16 and the higher. Yeah, that's true.
Really bad. Sorry for torturing this semester.
I said around 8 to 10.
8 to 10.
Around that, 8 to 10.
Well, 8 to 10.
Why is this a difference? I mean, because you guys should contribute to the group work evenly. I mean, everyone in the group should contribute. I'm not saying exactly equally, but yeah, what is difference here?
Not sure. I guess it's just like communication things.
Communication thing?
Like we have a slot.
Okay.
And I always schedule a room in Marston every single Tuesday.
So are you all guys there like every single Tuesday?
I'm there Tuesday and Thursday.
Every time,
Yeah.
every time.
Unless we have
I'm
like a
there.
report or something,
Every
in
time.
which case we're like in Marston coming back and forth.
So are you guys also there every time, every Tuesday?
I'm there every time Tuesday and Thursday. Yes.
It also is not just being there, it's contributing while you're there.
Okay. How should I say this?
Shoot.
I think we're kind of ready for.